Good morning. My name is Peter Mesdag. I'm talking to you from the Hague office of CGG in Holland. This morning I'd like to talk about model. Of course, Jason is specialized in seismic, and in many aspects of reservoir characterization you need to build earth models. Low frequency modeling for deterministic inversion is one example, but you can also think of making synthetic data sets. You can think of building stratigraphic frameworks for geostatistical work and that kind of thing. So there are many usages for model building in seismic reservoir characterization. My talk is divided into two parts. I'm first going to talk about the tools we have available in Jason, and then I'm going to talk about some workflows we've designed over the years working with seismic inversion. Just as a start, I'd like to tell you that I'm going to very briefly touch on the tools and workflows. So the tools for model building in Jason, which I'll talk about in the next couple of slides, are our Earth Model Builder. So it comes in two parts: a solid model builder and a solid model generator. The solid model builder just builds the framework, and the model generator actually fills volumes of data which you can use in the further processes. Next to the old Earth model, which has been in Jason for forever almost, we have something called EMFT, Earth Model, as also an Earth modeling program, which is a little bit more sophisticated than our regular Earth model, as it's linked to the reservoir through geocellular models. And then I'll talk a bit about multi-attribute well interpolation. That's built on a solid model. You can fill the layers based with guided by attribute information. And then I'm going to talk a bit about the model interpolator and FunctionMod. And all these tools we use regularly in our workflows for model building. So the solid model builder first. The input for the solid model builder can be 2D, 3D surveys, or mixed. You can mix 2D and 3D surveys or multiple 3D surveys. It's very flexible. What you put in is interpreted horizons, either in time or depth, and tide wells. And then as you build your framework, you can fill the framework with your well log information and control points. So you can control. You don't need wells. You can put in extra control points per layer, and they're treated as an extra well. And as an output, you get horizons, faults, envelopes, and the vertical components of your well curves and your control points and well weights. So starting with your seismic data, you'll have your well information, and you'll have some interpreted horizons and faults. These are then put into a framework, so you have to design it such that you have different fault blocks. So this is a QC where you look at the cross section of what you've built, and here I've built up the fault block starting from the bottom, working its way up. So block 1, block 2, and block 3. And how that translates into a framework is shown here. So the bottom, you see block 1, and then go working up, you go to block 2 and block 3. And this seems complicated, but what you really are seeing that your horizon names are transferred into the layer labels, and you define a stratigraphy, and that's mainly building up your fault block. And this is very flexible, because if we look at if we change a layer label, we're going to change the attribute of that layer and how the information is distributed over that layer. So for instance, I'm going to take in the third fault block, I'm going to take the 1 base layer, and I'm going to change the layer label into 2 base. So we have this framework where we can see that the layers on either side of the faults are connected to each other, but by changing that layer label, it actually changes the middle fault block, and all the information from wells or control points in the middle fault block is now used as a separate fault block, and it's not transported onto the fault blocks on the side. That's one example of changing a layer label. Another example is where we assign a trend fit. So now I'm going to take the second fault block, the middle one, and I'm going to change the one base trend. So here now you can see the trend fit interface. I've changed it into the 2 base. And what that does is, this is what we started with, and watch that the left-hand middle layer there, as I change the trend in that layer, you can change the shape or how the micro layers change. So that's just 2 examples of changing the framework table, and you can very easily think of more things to do with this framework building. Now, the interpolation methods are also important. All the interpolation methods, if you're using well control or you're using control points, are based on distance towards those control points. So we have various interpolation methods like inverse distance, locally weighted, natural neighbor, and also kriging, and you can put user weights in there, so you can completely design your own interpolation scheme. So that's quite flexible as well. So the solid model is actually used in many places in the workbench. You can, of course, it's used in the model generator to generate cubes of information. It's used in the model interpolator. The multi-attribute well interpolation works per layer, as defined in the solid model. You can use it for velocity conditioning. Of course, the viewers, they can use solid models, attribute extraction, if you want to run along micro layers, or if you want to extract attributes per layers. FunctionMod are phases of fluid probability, body checking, well tying, wavelength estimation, and of course the geostatistics use the micro layers as well as defined in the solid model. So there's a lot of usage for these structural solid models in the workbench. Here you see an example again, and it's showing the framework table builder again for a more simple case without faults. And you can see the same layering on the top right here. And one of the QCs is that you can look at how the wells are going to be interpolated, and that's shown in the bottom right here. So the wells are, of course, locally at the well position there. The weight of that well has a value of 1, and as you go to other wells, the boundary condition is that the weight is 0 there. So that's how the weights interpolate the information throughout the cube. And then you can go into a solid model generator, which is a separate program which actually builds the cube. Here's a cube of impedance information, P-Impedance information, which is extrapolated away from the well control. EMFT is another tool to build solid models and to fill your fault blocks. EMFT works on a single 3D cube only. It doesn't combine different surveys with each other. You can build complex faulted models with it. The framework, as I was explaining earlier, becomes quite complex if you have more than a couple of faults. So then we choose to use EMFT. Extra benefits of EMFT is that it's a link to geocellular models like the Trell and other applications, and it has a better handling of deviated wells because it doesn't verticalize the wells per layer. Then the next example is multi-attribute well interpolator called MAWI, and basically what you can do with MAWI is you can define attribute horizons to guide the interpolation of the 3D cube information per layer. And at the bottom here you see 3 maps. The first one is where we've used the regular Earth model, and you can clearly see that the bullseyes are local around the control points, and they doesn't look very geological because you're using distance criteria to decide on the values of the model. The middle one is how MAWI works based on the horizon which we gave to MAWI. It's an attribute horizon to guide the interpolation on the right-hand side, and you can see that it has been used in the interpolation, and it becomes much more geologic. Here we're only using one attribute horizon, but you can use multiple attribute horizons, and it will decide which attributes to use based on the well matches. So you can use multiple attribute horizons per solid model layer. You can it'll optimize the attribute relationships based on the well match through cross-validation. The selected attributes need to have some relationship with a parameter to be interpolated, of course, and extrapolations may extend beyond the well value range. Uncertainty information can be calculated. There is an option to do residual kriging at the wells because, of course, the attributes never completely define all the wells, and pseudologs are automatically generated from the interpolation results, so you can see how well the match is. Here's an example. We are using 3 attributes now. So it's a reef structure. So we have the seismic RMS of the top of the reef, and we have the time structure of the reef, and we have the thickness of the reef in time. Those are 3 attributes which we're going to put into the multi-attribute well interpolator. And you can see here, if we use all the wells, what happens. On the left-hand side again, there's the distance-weighted Earth model technology. There is in the middle is the MAWI results using those 3 attributes, and on the right is the same with residual correction. Because what you see in the middle result, it's because you have many more wells and attribute horizons, it cannot match all the wells, and therefore you have to do residual kriging to match the wells exactly. So if we now reduce the number of wells from here, we have many wells to only 3 wells, and that of course is much better defined by 3 attributes. You can see the Earth model interpolator on the left again, where you'll see all the bullseyes, and then the MAWI result in the middle, the raw result where it's matched the wells, and residual kriging on the right-hand side doesn't really do much to the result. So these are just a couple of examples of the MAWI interpolation. Then there's another interesting feature. We call that the model interpolator. On the map on the right-hand side, you see 2 3D surveys and a set of 2D lines. The larger 3D survey is electromagnetic survey. The middle 3D survey is the smaller 3D survey is a seismic survey with interpreted horizons and everything. And the 2D lines, of course, are also seismic 2D lines. What I've done here is I've taken the electromagnetic data, which is in depth on the larger survey, and I've interpolated it onto the smaller 3D survey and onto the 2D lines in one interpolation process. And what I'm showing here in the section on the left is shown in red as the line on the map. And you can see the background seismic of a 2D line, the interpreted horizons of the 3D seismic survey, and the electromagnetic response of the larger survey. The map, by the way, shown on the seismic survey on the right is actually an attribute extraction along a reservoir horizon from the electromagnetic survey. So this is quite a flexible tool as well. Then there's FunctionMod, and with FunctionMod it's like a mathematical spreadsheet program, and you can use any well curves, horizons, stratigraphic layers, or sample traces. You can do any mathematical function on those. You can use functions, tables, or you can even choose from any of the 400 predefined functions. You can use a solid model layer definition, or you can use time horizons, and you can use any number of input objects to define your functions. It's a very flexible tool, and we use it all the time to generate, for instance, models for synthetic forward modeling. So now to the second part of my presentation, where I'm going to talk about some workflows. These have been designed over the years that we've been working with seismic inversions, and most of them have been published as well, so the references will be given as well. I'm going to talk about 4 different workflows. First, I'm going to talk about including seismic velocities in the low frequency model. So we use seismic processing velocities to condition your low frequencies away from well control. This is a technique where we use rock physics models to map the velocities to the appropriate parameters. Then I'm going to talk about low frequency modeling, updating through body capture. I'm going to talk about 3D data-driven low-frequency modeling and 4D data-driven low-frequency modeling. So first, the seismic velocities. This is a paper from a colleague of mine and was shown at the EAGE in 2015. So you can reference that. What we start with is the velocity model coming from processing, and we've of course matched that at the wells, and it's transformed from RMS velocities into interval velocities. That's the basis we start from, and so you see that the velocity data shows a reasonable match at the wells, and we're not using any faults here because that would be too detailed for low frequency modeling. So we're making 4 steps here. We're going to make a conventional model. That means we're going to use our Earth model technology to interpolate wells based on horizons and stratigraphy. And then we're going to convert the seismic velocities to seismic elastic properties using regional rock physics equations. The seismic velocities are good up to about 2 or 3 hertz. And to get the part between 3 hertz and the lowest seismic frequency, you're going to use the conventional models. We're going to merge all the models together, so the lower frequencies from the velocities, middle frequencies from the conventional model. So this from the conventional model, this is the Earth model technology. Again, you're going to start with your well information and your stratigraphic framework. You're going to build well weights. In this example, we're using 2 wells, which are more or less in the northwest-southeast direction from each other. You see that the well weights themselves are shown in the middle picture here. You can see where the influence of the wells is in the model. So we're going to get elastic properties from this for density, P-impedance, and shear impedance. This is the conventional low-frequency model building. And to note, of course, are the well weights, which have a particular influence in this on the 3D survey. Then the next is the seismic velocities. We're going to start with our velocities, which were conditioned, and the seismic processing velocities, and we're going to map the velocities to density and to shear velocity using crossplots based on well control. So we're taking the shale background trend and we're mapping the velocities using the shale background trend to map it to both density and to S velocity. And doing that, we get our P impedance, S impedance, and density for the low frequencies. So now we have 2 sets of low frequency data: the velocity data, the seismic processing velocity, which are valid up to about 2 or 3 hertz, and then the well log data, which is valid up to the lower seismic frequency, and then the last parts coming from the inversion, the seismic data information, which fills in the higher frequencies. So the the well interpolation is the green area in here. The velocity data is covering the red area in here. And in that way we merge the data. So we've merged the models here, everything, the low frequency merged together, and we can use those in our inversion. Then looking at some maps extracted from those inversion models, also the low frequency models, you can see the top is just a well interpolation model where we use two wells which are like in the north, east, southwest direction. The bottom one is where we're using the seismic velocities. So you can see there's a clear trend in the seismic velocities which is imposed now on the density, P-impedance and S-impedance. If we change the scale in the top, you can clearly see the bullseyes again, which from the well interpolation model. So with sparse well data, the seismic velocities can better capture trends. Velocities need to be calibrated to well control, and we can use rock physics models to produce a consistent set of low frequency models for our inversion. Next workflow is the body capture workflow. So we do a first pass inversion with a simple trend, construct a polygon from well log cross plots, extract bodies from the inversion, replace the values within the bodies in the trend, and merge the new trend or re-invert with a new trend. So we start with this is a synthetic example. We start with a simple background for, here we're using P-Impedance and Vp/Vs. So this simple, just a regional trend model. Then we do a first pass inversion using the pre-stack inversion using the seismic. So the top is the inversion result, and you can clearly see the side lobe because we're not putting in the low frequency in the background trend, and the true model is at the bottom. And there's two extractions through the bodies on the right-hand side, where you see the true model is the blue curve and the inverted model is the red curve. You can clearly see that we are not matching the values, and we are seeing also very strong side lobes next to our contrasting layer. With this, we can do body capture. So we can cross-plot well log information and put a polygon around the area where we think our bodies are, and that actually shows up the bodies you see on the right-hand side here. Within those bodies, we can put in, for instance, a sand trend, or use rock physics models to put in some realistic values for the P-Impedance and the Vp/Vs. And that's done here, so we superimpose that information on the low-frequency background trend, and then we re-invert, and now you see the inversion result is much cleaner. Both the P-Impedance and the Vp/Vs, they match the true model, and you don't see any side lobes anymore. And that's shown with the extractions on the right, where the true model is the blue again, and the newly inverted model is the red curve, and you're only missing some high frequencies, so you see the high frequency jitter, but the low frequency mismatch, the big side lobes have disappeared. So if you would have used the correct trend, you only see a very slight change in the inverted model. So low frequency model can be updated within the reservoirs using the sand trend model. For thicker packages, manual interpolation is required to map the sand bodies. Side lobe effects are highly reduced using the updated low frequency model, and sand trends may be adjusted for fluid scenarios, and the concept is relatively simple and fast to implement. The next example is a 3D data-driven low frequency model update. First perform a first pass inversion, we're using a simple trend, interpret the top and the base of the bodies, so this is a interpretation. You extract the contrasts over the interpretations, replace the original well log interpolated values with the new ones, and merge in the new trend or re-invert. This is an example from published in the EAGE in 2010. This is where an inversion where we only used a well interpolation, and a new well was drilled on the inversion results, and it came out with a too high impedance or actually a too low porosity. So that was a reason to update the inversion results. What you're seeing here is a Zechstein. It's anhydrite. The blue, it's a high contrasting layer. And what's happening is that the anhydrite is interleaved with shale and locally changes in its impedance values at the seismic scale. And the well interpolation is not sufficient to capture those changes, and that's why we designed this new technique. So this is the predicted porosity, and you can see that the new well has a too low porosity based on the inversion results. So what we're going to do is we're going to interpret the Zechstein anhydrite. So the top and the base is very easily interpreted there, because you can very clearly see the anhydrite on the first pass inversion. And what we're going to do then is to extract the contrast over every one over this interpretation. So you take the value just above your interpretation and the value just below the interpretation. The difference between those two is the contrast. And so step one is where you extract the contrast over your interpretation. Then you have your well interpolation for the reservoir layer just below the Zechstein, and that's called that reservoir layer has a very slow varying P-impedance, and you superimpose the extracted contrast on the background P-impedance and re-merge that into the Zechstein anhydrite. So what you have is your initial trend model, initial low frequency model, and the updated trend model, and the difference is shown on the right hand side. With this newly updated model, we rerun the inversion, and now you see that we have changed due to changing the Zechstein layer, we've changed the side lobes of the Zechstein, and they no longer influence the values within the reservoir section. And you can see the black is the extracted average acoustic impedance for the reservoir layer or ligands. The black is from the original inversion, and the red is from the newly updated inversion. You can see that the P-impedance at the newly drilled well indeed has a slightly higher value because we updated the low frequency model. And of course the porosity mapping from that P-impedance has changed the map in the reservoir as well, and you can see the lower porosity of the newly drilled well. You can extract maps, and before and after you see there's a lot more consistency in the maps coming out of this updating of the inversion. These are the map of the average porosity in the rod ligands. So for the is the next and the last example where I'm going to use a similar technique as described in 3D in the previous slides, but now I'm going to update for the low frequency model. And the reason why we can do this in 3D and in 4D is because our inversion results are actually calibrated to well control, and we can assume that low frequency contrasts are similar to the seismic derived contrasts. So here we're going to invert different seismic. We're going to take the stack information from the monitor and from the base, or the partial stacks from the monitor and base, and subtract them, and then do an inversion on that different seismic. We put the top from the base the bodies like we did in the Zechstein case, and then extract the contrasts over the interpretation and paint those contrasts within the bodies. We did that in 3D in the previous case, now we're going to do it in 4D, and then we're going to merge the new trends into the different inversion results. This is a recent example. It was published in the Leading Edge in 2015, and what you're seeing here is the band-limited change in P-Impedance and the band-limited change in Vp/Vs, so it's the results out of inverting the difference seismic. And you can see that this is a heavy oil case where it's these are gravity-assisted drainage steam chambers, and you can see there's a P-Impedance increase at the top of the steam chamber and decrease at the bottom of the steam chamber, and there's the Vp/Vs decrease at the top of the steam chamber and bottom. And this can vary depending on the production cycle, where you are in the production cycle. So what you do is you interpret on your first pass band-limited time-lapse P-Impedance and Vp/Vs, and then you measure the contrast over those interpretations. So you extract the values just above the interpretation and below the interpretation, and that will be the contrast over that interpretation. And you make a low-frequency model. And in 4D, the low-frequency model is the change in P-Impedance and Vp/Vs between base and monitor. Of course, the change is zero everywhere outside your steam chambers. And what I've done here is painted a linear trend from the top, putting in the top contrast at the top and the bottom contrast at the bottom. And merging this with our band-limited inversion results, you can see the full band time-lapse P-Impedance on the right-hand side and the full band time-lapse Vp/Vs. And these are now much easier to interpret for people who are not really well versed in seismic band-limited data, because the reservoir engineer can't make sense of the left-hand pictures, but he can make sense of the right-hand pictures. So that's the last workflow, and that ends my presentation.